In this video, we're going to finish up section 7.6, which deals with some multi-step factoring and choosing what factoring method is needed for a given problem. So we are now on to example 7. Okay, so our general thought process when we're factoring is we always look for a GCF first. So is there a GCF in number 7? Well, I see that there's a 2 in common, and both terms also have a y, and the smaller of the powers is y to the first. So our GCF here is going to be 2y, and we are going to divide and drag the 2y. So now we have 2y on the outside times the quantity. Well, the 2's will cancel, the y's will cancel, so we've got x squared, and then the 2's cancel, minus y cubed divided by y to the first is y squared. So far we've done one step of factoring. We pulled out the GCF. Now we double check that there's no more terms in common, which there aren't, and now we're looking to see if we have a special pattern on our hands. Is this a difference of two squares or a perfect square trinomial? Well, with these, difference of squares is a 2-termer. Perfect square trinomial has 3 terms. Well, inside we've got 2 terms, a minus sign, and they are both perfect squares. So this is a difference of squares. So for our difference of squares pattern, we take the square roots of each term. Make sure, first of all, we drag down the GCF. That was a 2y, not a 2x. And now the factor pattern for DOS, difference of squares. 1's plus, 1's minus. So we do x plus y times x minus y. And that is now done. Okay, because we are down to first powers with each of these, and there's no common terms. Let's take a look at number 8. 12b cubed plus 48b squared plus 48b. So starting off with our first question, do we have a GCF? Well, they're all even numbers, so we've got that going for us. And if I look at my smaller number, 12, does it divide evenly into my other 2 numbers? Does it divide evenly into 48? Well, yes, it does. 48 divided by 12 is 4. They also all have b's. So my GCF here is going to be 12b to the first, because b to the first is the smallest power of our b's. So we're going to divide and drag a 12b. So now I have 12b on the outside. And what remains on the inside, well, 12 divided by 12 is 1. B cubed divided by b to the first is b to the second. Plus 48 divided by 12 is 4. B squared divided by b to the first is b to the first. Plus 48b divided by 12b, well, the b's are going to cancel, and 48 divided by 12 is 4. Now we always verify there's no more GCF, nothing else, that all 3 of these terms share on the inside. And now we ask, is this a special pattern? Well, it's not a difference of 2 squares because there's 3 terms. Is it a perfect square trinomial? Well, let's check it out. Perfect square trinomial pattern. We need a perfect square in the front, a perfect square, a positive perfect square in the back, and the product of their square roots times 2, double the product of the square roots, needs to equal the middle term. So let's check it out. Square root of b squared is b. Square root of 4 is 2. If I do 2 times b times 2, do I get the middle term? Yes, I do. So this is a perfect square trinomial. And as a reminder, what is our perfect square trinomial pattern? Well, first let's drag down the GCF of the 12b. And now the perfect square trinomial, I take my square root of the first, the sign between my first two terms, and the square root of my last. Goes in parentheses, quantity squared. We could also use McAb to factor the b squared plus 4b plus 4 due to the fact that it is a quadratic second power trinomial, 3 terms, with a leading coefficient of 1. Okay, so then you'd say b plus 2 times b plus 2. Okay, so this is also McAb. Still get the same exact answer. Let's check out number 9. First question, is there a GCF? Well, 4, 12, 72, they're all even numbers. Does 4 go into the other 2? Well, 72 divided by 4, yeah, that's going to be, let's see, 18. So GCF is going to be a 4 because there is nothing else in common. There's no y's in all 3 of the terms. So we're going to divide and drag a 4. So now we have a 4 on the outside. Drag down what remains. The 4's cancel. Left with y squared. 12 divided by 4 is 3, so plus 3y. And minus 72 divided by 4 was 18. So now we have to determine, is this any of our special patterns, because there's nothing else in common. Well, it's not a difference of 2 squares because there's 3 terms. Perfect square trinomial, well, I have a perfect square in the front, but I do not have a positive perfect square in the back. This is going to be McAb because we have a quadratic trinomial with a 1 in the front. So we now need to determine what multiplies to be C, negative 18, and adds to be B, positive 3. So in order to multiply to be a negative, I need a positive and a negative. If we're adding to be a positive, we need the bigger number to be positive. So negative 1 times positive 18. Negative 2 times positive 9. This is where we're using our calculator. Negative 3 times positive 6. Okay, and there's actually no more factor pairs that will multiply to be positive, or multiply to be negative 18, add to be positive. So which one of these factor pairs, if I add them, will give me a positive 3? Well, that's going to be the negative 3 plus 6. Okay, so here's our winner. Therefore, my factored answer, I need to drag the 4 down. The GCF needs to not be forgotten. And now I need, it's actually a y, variable is y this time, a y in the front of both. One's minus 3 and one's plus 6. And we are fully factored. These are all down to the first power and no common factors among. Okay, we've got 3 more. In number 10, x to the 4th minus 9x squared. Is there a GCF? Well, yeah, they both have x's. Smallest degree is x to the 2nd. So we're going to divide and drag an x squared. When I do that, I then have x to the 4th divided by x squared is x squared. minus the x words cancel in the back, and we just have 9. No more terms in common on the inside. Is it a special pattern? Do we have a difference of 2 squares or a perfect square trinomial? Well, I see 2 terms. I see a minus sign, and they are both perfect squares, so this is a difference of squares. So here comes our work and our factor pattern. I need to take the square root of each. Square root of x squared is x, square root of 9 is 3. Drag down that GCF of the x squared on the outside. And then our difference of squares is x plus 3 times x minus 3. Number 11, 2p to the 5th plus 10p to the 4th minus 12p to the 3rd. Do they have any common factors? Well, all the numbers are even. Smallest number that we have here is a 2, and 2 does divide evenly into 10 and negative 12. All 3 of our terms also have a p. The smaller of our powers is p to the 3rd. So our GCF that we need to clearly state is 2p to the 3rd. So we're going to divide and drag the 2p cubed into everything. Not forget the drag piece. Okay, so the 2p cubed is on the outside. The 2's cancel. P to the 5th divided by p to the 3rd will give us p to the 2nd. Plus 10 divided by 2 is going to be 5. And p to the 4th divided by p to the 3rd is just p to the 1st. And then minus our p cubes will cancel, and 12 divided by 2 is 6. So we now ask ourselves, is there another GCF? Nah, nothing else in common on the inside. Is it a difference of 2 squares or a perfect square trinomial? Well, it's 3 terms, so perfect square trinomial is the only option. But I've got a perfect square in the front, but I don't have a positive perfect square in the back. So not a perfect square trinomial. This is, however, a McAb, where we have a quadratic trinomial with a 1 in the front. So we're going to go with that. So now we have to determine what multiplies to be negative 6 and adds to be positive 5. So we're going to need a positive and a negative in order to multiply to be a negative. And the positive needs to be the bigger one in order to add to be a positive. So negative 1 times positive 6 or negative 2 times positive 3 are our only factor pairs of negative 6 that will then add to give us a positive. Well, the winner is going to be negative 1 plus 6 to give us that 5. So we need to make sure that we drag down that GCF of 2p cubed. And now I need my 2 binomials, each with a p in the front. And one needs a minus 1, one needs a plus 6. And we cannot go any farther. No more GCF on the inside of either factor. And we're down to the first power. All right, last but not least, here we have number 12. Number 12, we've got 2x to the 8th minus 2. Do we have a GCF? Well, yes. They both have a 2. So we're going to divide and drag a 2. So we've got the 2 on the outside. And then, well, the 2's are going to cancel, so we're going to be left with x to the 8th. And when I do 2 divided by 2, yeah, they cancel, but 2 divided by 2 is 1. So if everything cancels, you're left with a 1. So now we're looking, do we have a special pattern? Do I have a difference of two squares or a perfect square trinomial? Well, this is two terms. There's a difference, and they are both perfect squares. Because that 8th power is an even number, I can take the square root of x to the 8th. So we've got a difference of squares. So this one's going to be lots and lots of fun. So the square root of x to the 8th is x to the 4th, because x to the 4th times x to the 4th gives us x to the 8th. Square root of 1 is 1. So I can only do one square root at a time. So I need to drop down now, drag the GCF of the 2, use my difference of squares factor pattern and write it as x to the 4th plus 1 times x to the 4th minus 1. Now, especially due to the fact that I have exponents other than 1 here on the inside, I want to continue to address, do I have anything else I can do? There's no GCF on the inside of either, but looking at these special patterns, I have a difference of two perfect squares here again with that back factor. This x to the 4th plus 1 can't be touched because that's a sum. So let's drop down our square roots of x to the 4th minus 1. So the square root of x to the 4th is x squared, because x squared times x squared is x to the 4th. The square root of 1 is 1. So I need to drag down everything before it. So I've got the 2 times x to the 4th plus 1. But now this x to the 4th minus 1 is going to become x squared plus 1 times x squared minus 1, because we had more DOS. And hey, guess what? We still have exponents inside, and I have another difference of two perfect squares. So we've got another DOS here at the very end. Square root of x squared is x, and the square root of 1 is 1. So here comes our grand finale. We've got the 2, that was the GCF that drug all the way along all these steps. I've got the x to the 4th plus 1. We've got x squared plus 1, neither of which were able to be broken apart any farther. And then this x squared minus 1 factors with a difference of squares of x plus 1, x minus 1. And now, due to the fact that these are now down to x to the 1st powers and there's nothing else in common, this multi-step problem is now done. Okay, so we had 1, 2, 3 difference of squares factoring that needed to happen. Okay, but we can only drop down and factor and take that square root 1 at a time.